attention that you decided to come back to the next part of my talk. I hope it will be second and the last. I will speak about polynomial and elliptic Poisson algebras, and mainly I will speak about elliptic algebras today. So today my talk will be based on my paper with Sasha Adesky, which was published in 2008, old paper. And on one paper, I decided that the second paper, I have no time to speak. So I will speak about my paper with my former PhD student, Serge Tanya-Pilap, who is now, unfortunately, for mathematics, and fortunately for him, works for Credit Suisse in Zurich, and Giovanni Artenzi, who works in Milan Bicocca University. And the biggest part of my talk will be based on my paper, my survey paper in a recent book of Buchstaber and other editors, recent developments in integrable systems and related topics of mathematical physics. It was in 2018, published by Springer. Before I start to speak about main subject, I just want to say that my interest to this was very, very modest. I wanted to understand so-called blue preprint of Boris Fegin and Sasha Adesky, which is in Russian, it is called Sklyanin algebras associated with elliptic curves. Unfortunately, this preprint never appeared in other form, neither in Russian nor in English. It is so-called Kiev blue preprint because it was published as a preprint of Institute for Theoretical Physics of Bogolyubov of Ukrainian Academy of Science after a big conference of '88, and it was published in '89. And this was the first big publication about generalization of Sklyanin algebras. You remember I spoke about Sklyanin algebras with 3 and 4 generators, and Adesky and Fegin proposed a very interesting generalization of this class of algebras for any number of generators, and with many more general properties and geometrical and algebraic interesting features. So that's why these algebras are often called not Sklyanin algebras, but Sklyanin-Adesky-Fegin algebras. And this blue preprint was the only place where they formulated property of Sklyanin algebras with 5 generators. Why 5 is much more interesting than 3 and 4, though 3 and 4 are very interesting cases as well. You have seen that they are interesting, but because they appeared in very nice period of integrable system dream world. And 5 is a quite special number of generators because it is the first time when we meet with 2 absolutely different, though with very similar by properties, but different in many senses elliptic algebras. And this phenomenon doesn't exist for n equal to 3 and for n equal to 4. And also this is n equal to 4. And also this is an interesting moment, which was not, fortunately for me, because it was my only small observation additional to this blue preprint, how these algebras are related to so-called Horrocks-Mumford geometry and Cremona transformation in P4. That's the main subject of my talk. So I will speak about this in the second part of my talk. I start with last example, which I had no time speak last time, but I can't avoid it because Now it is very popular as a subject. So I want to show you the last example of polynomial algebra, which is not Sklyanin Odesky-Feygin, but this algebra, polynomial Jacobian algebra associated with number structure, Poisson structure, which correspond to this Casimir polynomial. And it is interesting that this polynomial generalize Sklyanin with three generators, because if you consider it attentively, you see that this non-homogeneous function phi has full cubic term, quadratic terms with coefficient epsilon 1, epsilon 2, epsilon 3, linear terms with coefficients omega 1, omega 2, omega 3, and free term omega 4. So we have many parametrical family of Poisson structures in three-dimensional polynomial algebra. And if you put all these coefficients epsilon and omega equal to 0, then you obtain a homogeneous cubic. And if A equal to B equal to C, then it is exactly the case of Artin-Tate-Sklyanin algebra with three generators. You can ask why it is interesting to consider the other cases. The other cases it is interesting to consider because if A, B, and C are equal to 0, then the cubic phi correspond to so-called Dubrovin, Ugalia, Nelson-Ridge Poisson structure. And this Poisson structure, very interesting example, which relates first of all to Poisson structures on the monodromy data of Mendeleev linear systems, namely if all these coefficients epsilon 1, epsilon 2, epsilon 3 equal to 1, and omega 1, omega 2, omega 3, omega 4 are considered like parameters, then you obtain the cubic which corresponds to Mendeleev 6. And if epsilon might be O0, O1, and if they are equal, some of them equal to 0, and some of them equal to 1, then you will obtain the cubics which correspond to the confluented linear systems from Mendeleev 6 to Mendeleev 5, Mendeleev 4, etc. And the coefficients omega, they play the role of parameters, but in fact they are traces of monodromies around poles in the case of Mendeleev 6. And in generally speaking, these coefficients, they contain also some data entered in the Stokes phenomena. I had no time to be very precise here. I just want to show you this example. And this example is very interesting because you can marry the Sklyanins and generalize Sklyanin, because for Sklyanin, A, B, and C, they are all equal to some constant. And here they might be different and they might be 0, some of them. And it is also very interesting, by the way. Anyway, this is the last example before going to main subject of the second part. So I remind you that we have considered the first simplest and very interesting in its turn Artin-Tate Sklyanin algebra with three generators. This algebra associated with a normal cubic elliptic curve, which is embedded in projective space P2 with the help of sections of a line bundle of degree 3, which usually people associate with so-called three theta functions. And this function, Casimir function of this Poisson structure, which denoted by big P, this is a Hesse cubic given by this embedding. So the corresponding brackets are Jacobians, corresponding brackets are purely quadratic, and the constant k here depends on the modulus of the corresponding elliptic curve y. A symplectic foliation is has the following type of leaves. Origin, x1, x2, x3, the zero-dimensional leaf. The whole curve without zero, and if you fix non-zero constant lambda, then also you have a symplectic leaf of dimension 2, y equal to lambda. So everything is here very explicit. And also the nice property of this bracket, immediately you can check that this Poisson structure is invariant with the so-called Heisenberg group with H3 Heisenberg group. This group of transformations which shift the index of the coordinates and multiply the coordinates by root of degree 3 of unity. So you have this group generated, and we will consider how to generalize it, invariance property, and what is the consequence of it for other elliptic algebras, because they are also admit this property. So polynomial Poisson algebras, which we will consider, usually denote by small q sub n k, where n and k are pairwise mutually prime integers integers n and k. So you have a family of Poisson structures dependent of two natural numbers n and k, and they have this notation because usually the most interesting object was their quantum, so-called quantum analog, namely associative quadratic algebras big K and K, which is also called elliptic Sklenin-Odesky-Feygin, but quantum algebras. And this family of associative quadratic algebras I will briefly describe. I have no time to go to this theory because this is a huge theory, but I will just describe the property of these algebras because my object, namely polynomial Poisson algebras, they are quasi-classical limit of it. So here we have, as usual, y will, through all my talk, will be an elliptic curve, a normal elliptic curve of some degree, and this degree will be number n. And if we take the parameter eta, which is a point of elliptic curve, taking this parameter equal to 0, this algebra is nothing but the usual polynomial. So this class of algebras, this is a deformation with the help of eta of polynomial algebras within generators. But this deformation is quite special because eta is a point on the elliptic curve, so this deformational parameter should know something about abelian structure of your elliptic curve. How it looks in generators and relations. So if my curve given by this lattice gamma, so this is a quotient of complex plane by gamma, then we fix the modulus tau with the imaginary positive part. So this algebra Q and K has n times n minus 1/2 generators, and these generators satisfy to the following quadratic homogeneous relations. And coefficients of these relations are expressed in terms of theta functions of level n, and these theta functions of level n are associated with this gamma lattice. So these are quasi-periodic functions. I will not precisely describe this class of theta functions. It is very well described in the literature. I just, you can consider this like a constant coefficients in zero, and so it is not usual theta function of Jacobi type, though it relates somehow, because you see it is not usual Jacobian function equal to zero in zero, but these are not. And the property of this algebras is the following. You can think about this algebra like a graded algebra with graded components denoted by Q sub alpha. Zero component is just constant. Q1, it's a vector space of dimension n. Vector space of dimension n. And usually this vector space of dimension n can be explicitly described in terms of this theta function of level n and lattice gamma. The operation in this algebra, which is denoted by star, satisfy the usual property of graded associative algebra operation. So the product of elements of degree alpha and beta gives you elements of degree alpha plus beta, and the corresponding algebra has the following nice property. So the Poincaré-Hilbert function of this algebra can be explicitly written like 1 over 1 minus t to n, which means that your algebra satisfied the Poincaré-Bergov-Witt property. Then the different values of second parameter k, if they are satisfied to this relation, k times k prime has the same rest 1 by module n. So this k comparable with k 1 over k by modulo n. Then these algebras with q and k and q and k prime are isomorphic. All these properties are was enlisted in the paper of Odesky and Fagin, but I want to say that full and rigorous demonstration of all these properties was obtained in general case only very recently in series of papers Paul Smith and his collaborators in 2017, 2018. It doesn't mean that Odesky and Fagin did, but demonstrations they or never published or just published in very, very brief and approximative way. So all these algebras satisfy to this invariance property. It means that if you have the n root of unity epsilon, then the transformation gives you automorphism of your algebra Q and K Y eta. And then also if you want to think about this algebra like a deformation quantization of something, then the initial algebra, polynomial algebra with n generators, corresponds to eta equal to 0. So what it means? It means that if we take eta goes to 0, then we obtain Poisson algebra q small n k of y, and this algebra satisfy to these bracket relations, which can be obtained by cumbersome but straightforward computations from the quadratic relations which I showed you from these quadratic relations. By cumbersome but straightforward computation gives you this quadratic homogeneous brackets between xy, xj. And it is interesting that for n equal to 3, these relations are explicitly, unfortunately, you know, because of this, I wanted to show you how to get from this relation for n equal to 3, the relation of Sklyanin, Tate, Artin Tate, where is this? This one. How this k relates to theta function. I just prepared explicit formulas for this, but I can't show you at this moment. Maybe next possibility will have. I will have next possibility to show you. So this the formula for brackets, and then also very important property which we proved with Adesky in our paper, which I quoted last time in Theoretical Mathematical Physics 2002. If we have this Poisson algebra Q small sub n k of y, then this algebra has L Casimirs, and these L Casimirs, they are the number of L. It is a biggest common divisor of n and k plus 1. This Casimirs denotes by p sub alpha, and each Casimir has a degree n divided by L. This is a theorem which we proved with Adesky. For example, if you have this theorem, then you can easily check that for n, for k equal to 1, and n even, number of Casimirs always 2. If k equal to 1 and n is odd, number of Casimirs always 1. So centrum of Q n 1, or two-dimensional or one-dimensional. It is important because n equal to 5, the first case when the centrum has dimension 1 and different Casimirs for different algebras. And also we prove with Adesky the following strange but interesting result. If we have algebra with, if we have algebra with even number of generators, then this algebra with even number of generators and k equal to 1 has m commuting elements, each element of degree m. So we have a kind of abelian subalgebra of m elements degree m. And as a corollary, we have the same result for Poisson analog of this algebra. It means that we have a kind of algebraic integrable systems which associate with this Poisson bracket. It would be interesting to find a precise physical example of the corresponding integrable system. So now we go to the main subject of my talk, the five-dimensional case. So this is, as I told you, this is the first case when we have two different Poisson tensors which generate this Adesky-Feygin construction. And also, this is the first time when the corresponding elliptic curve embedded by, with the help of theta function on the projective space of degree of the dimension 4, this is not a complete intersection. So Artin Tate and Sklyanin for n equal to 4 was were two examples of singularities of simple singularities. But here we don't have a complete intersection, and we have to describe embedding of my quintic elliptic curve to P4 with the help of very beautiful geometric construction which goes back to Felix Klein, so-called Klein CZG5 quadrics. I will show you a little bit later this And also this interesting feature of my algebra is that algebra Q51, it is in three Hamiltonian algebra. This is a partial result which Adesky proved for any algebra Qn1, which is always three Hamiltonian. But about Hamiltonian, bi-Hamiltonian or three Hamiltonian properties of the second algebra Q52, it is still open question. It is still very obscure. I know some examples of bi-Hamiltonian structures, but they are very, very strange for Q52. I mean, they exist only for special choice of parameters. Now, I want to say that these algebras, they quasi-classical algebras, in contrary to quantum big Q, they don't depend on point on elliptic curve, but they depend on this elliptic curve implicitly. And how implicitly we will see. So with 5 generators, algebra with 5 generators, this is also the first very good example. And also I know a few examples for n equal to 7, I have checked it. And this first example with a prime number of generators. And then in this case, normal elliptic curves are given by Pfaffians. As I told you, they are not local complete intersections, but this embedding given by some quadric relations. And these quadric relations are Pfaffian of some skew-symmetric matrices. Let's consider explicit formula for Q51. These 5 generators, I index I goes to from 0 to 4 or from 1 to 5, whatever you want. So it's a 5 periodic index. And you have brackets between elements with this neighbor indices and bracket between elements with index which differ by 2. So parameter k, it is like in the case of Art and Tate, this parameter can be explicitly expressed in terms of theta functions of level 5. So we have degree 5 quintic y tau, and this k depends on this tau through these theta functions.
Sorry, may I ask a question, Volodya?
Sure, sure.
Женя Ферапонтов speaking.
Да, Жень, конечно.
Volodya, so, but your bracket depends on k in a rational way. Why is there anything elliptic here? It looks like, okay, it depends rationally. How do I see that something is elliptic?
What do you mean? Because k, here, k, in fact, k, it is a rationalization. You can write it. You will see. I will write it a little bit later. I will write this in terms of parameters on P1. It will be related to some elliptic fibration with a base P1. K, it is, you can, instead of k, to write lambda over mu, where lambda and mu are homogeneous coordinates on P1.
But the dependence is rational on k, right?
What do you mean? This parameter, yeah. It is a theta function. And they are depends on tau. On tau, they depends elliptically, if you want.
Yeah, but it depends rationally on k. All right, so it's okay.
No, Jenny, look here. You that's because what I suppose that it will be something. Here you see it's linearly dependent on k and what?
Right.
Right?
Yes.
But you see the elliptic curve.
Okay.
Huh? Or not?
Yeah.
So you agree that k it is something elliptic.
So okay, here no, but still the Casimir. All right, so Casimirs then will be elliptic somehow.
Yes, I will show you. I will show
Right.
you not Casimir's but Pfaffian's, which depends on this K explicitly.
Okay, thank you, Volodya. Thank you. That's fine.
I explained
Yeah,
a
yeah,
little bit.
thank you.
Okay, so this is the first algebra, and it is very interesting to get the centrum of this algebra, and this centrum is given by the quintic expression, homogeneous quintic with 5 generators, and this is also depending on K, and you see also depending, like you say, rationally. Well, and this quintic belongs to the so-called the class of Schoen quintic. The level of this quintic, zero level of this quintic, it is a threefold, which is a Calabi-Yau threefold, very famous in mirror symmetry. And the same story is for Q5, 2. So of course, the brackets are slightly different. They are the same type. And you think that the algebra should have the same property, but it indeed, it is almost the same, but not completely. I don't have time and possibility to go in details, but recently, in the last maybe 2-3 years, there were 2 papers of Brent Piem and Marco Gualtieri, and then Brent Piem alone, where they describe very, very precisely the difference from the viewpoint of algebraic geometry of these 2 algebras, Q5.1 and Q5.2. And it is a little bit a part of my story, so I will just to stress that these algebras are quite different. They are both logarithmic, symplectic, but the symplectic foliations of these algebras are different. And you will see symplectic foliation, foliations I will explain. You will see why they are different. So very important property of these algebras, I'll go now to the more or less general property. If you have nth Heisenberg, nth level Heisenberg group, in its so-called Schrödinger representation, this group generates by 2 generators, sigma and tau. So sigma, as I told you before, it is just a shift of index. And tau, it is a multiplication by root of unity. And then this group has the order n2,3, and this is a central extension which belongs to this short group suite. And this un, it's a nth group of unity, and z sub n times z sub n, it is a just a z mod nz times z mod nz. So this property of generators of some polynomial algebras to be Heisenberg invariant, it is very, very restrictive property. For example, in the paper, which I have no time to explain, we proved with my student and Giovanni Artenzi, we proved that if we have polynomial quadratic algebra, which is polynomial quadratic algebra, which is the Heisenberg invariant, then it is elliptic quadratic algebra. So it is almost very, very restrictive property, which singled elliptic quadratic algebras among all other polynomial quadratic algebras. We have proved it for n equal to 3, for n equal to 4, for n equal to 5, and for n equal to 6. But it is probably true for any n. Okay, now what I told you that this algebra depends on elliptic curve, not very explicitly, but implicitly it can be described. This dependence can be described in the following way. This elliptic quadratic Poisson structure is nothing but quadratic Poisson structure on projective space of dimension n-1, so n, q, and k. And this structure, it is a structure, this projective space can be identified with the moduli space of vector bundle of degree n and rank k plus 1 with the choice of parabolic structure. So we have a flag in the vector space of dimension k plus 1. So if we fix this flag, we have a parabolic structure vector bundle on this elliptic curve. This moduli space can be described as a moduli space of the following exact sequences. So this vector bundle with parabolic structure can be inscribed in this exact short sequence. So psi 0, 1 and psi nk, it is notation for due to ATIA description of vector bundles over elliptic curve. So psi 0 or 1, it is just a regular function on your curve. And psi nk, it is a denote degree n and rank k indecomposable bundle, which was proven by ATIA, exists on elliptic curve. And then space of equivalence of these short sequences, it is nothing but projective modulus, projective space of degree of dimension n-1. And this Poisson structure on this modulus space is exactly my quasi-classical limit of algebra structure of Q and K. This is the theorem of Adesky and Feygin, which was proven in 98-99 in Japanese reprint, and then this was published 7 years later in some of translation of American Mathematical Society. And this demonstration of this theorem is based on ATIA description of vector bundles on elliptic curve and R-matrix properties. I have no time to go into details, but this moduli space of parabolic bundles, they are exactly this CPN minus 1 and structure on CPN minus 1. This is my quadratic elliptic structure. Another description was done by Sasha Polishchuk, also algebraic geometric. So he considered moduli space of so-called stable triples. And these stable triples, E1, E2, phi, E1, E2 vector bundles with additional condition of stability. And phi is a morphism and homomorphism between these two bundles. So if we have a special choice of E2 OY and E1 E, then we obtain exactly Adesky-Feygin description of our structure. So he constructed symplectic or structure on the space of these triples. This symplectic structure on the open dense, so it is Poisson structure mainly. But in special choice, he got this Adesky-Feygin description. And also, he discovered very interesting relation between two moduli space. If between k and phi of k, where phi is this rational function, so this phi of k is a function 1 over minus k plus 1. So it is a kind of rational number. But if you take the relation between k and phi of k, then this relation modulo 5 gives you the isomorphism which Polishchuk proved. So if we take our moduli space of Adesky-Feygin, MNK, parabolic structure vector bundle of degree n and rank k, and take this phi of k can be considered like an integer which has the same relation with k modulo 5. For example, if you have n equal to 5, then this rank phi of k gives you 2. So you have a birational transformation. Q5 of 1, this is the modular space of M and K. For K equal to 1 and N equal to 5, you have Q5, 1. And if you have this R prime, which relates to phi of K modulo 5, then you obtain M, N, it means 5, and this phi of K, it's 2. So we have this birational transformation of Polishchuk. And my goal was to describe explicitly this birational transformation as a Cremona transformation, which might be interesting for Jenny. So the theorem which is known in this blue preprint by Odesky and Feigin in quantum case is the following. The quantum algebra, which corresponds to Q52, is a subalgebra in Q51 generated by 5 elements with 10 quadratic relations. In its turn, Q51 is a subalgebra in Q52, also generated by 5 elements and by cubic relations. And the composition of this embedding, so you have embedding of Q51 to Q52 and then to Q51, on the level of generators, it is just multiplication by this Casimir, by this, which I showed you, by this quintic. And the composition of Q52 to Q51 to Q52, it is just multiplication by the second Casimir. And it is nothing but, it gives you very explicit description, which was generally described Odesky in this, in Feigin in this blue preprint, of symplectic leaves of these two algebras. So algebra Q151 has 0-dimensional, 2-dimensional, and 4-dimensional symplectic leaves. 0-dimensional is not very interesting, but 2-dimensional symplectic leaves, it is just a cone over this curve. And this cone can be considered like just a chord or secant variety of this elliptic curve. In the case of elliptic curve, the first secant variety, by definition, it is just the very elliptic curve. And 4-dimensional symplectic leaves, they are cones over unification of all chords of elliptic curve. So it is a second variety. I want to draw your attention the difference between, I have various notation, secant variety, and this is a C2, so a second variety. And the first secant variety, it is just elliptic curve. So we have two non-trivial 2- and 4-dimensional symplectic leaves for algebra Q51. And these leaves, they are hypersurfaces of this unique Casimir, which we saw, this big quintic. So 0 level of this Casimir gives you the symplectic leaf of dimension 4 in 5-dimensional affine space. What about Q52? About Q52, we should consider more interesting and more complicated algebra geometric object, so-called elliptic scroll. Scroll, it is, as far as I understood, it is just an old-fashioned name for ruled surface. So this is elliptic ruled surface, which associated with the symmetric product of the initial elliptic curve in P4. And the description of 4-dimensional leaves. So we have 2-dimensional leaves. It is just like in the case of Q51, just a cone, but not over my curve, but over this elliptic scroll S2 of my curve. which I denote by x. And the description of four-dimensional leaves, it is based on the notion of so-called 3-second variety. It is also elliptic surface, which associated with my ruled surface symmetric square of elliptic curve. And this 3-second variety is just nothing but the union of all lines in this scroll. So, which is a quotient of the Cartesian product by Z2. So we can consider the pairs of points psi1 and psi2. So we fix psi, and then we have a curve which corresponds to this fixed psi. So we have all this union of all these lines passing by these pairs, psi, psi1, psi, psi2, and we have this quintic hypersurface which we obtain by this unification of all this line. This unification is called 3-second variety, and it is given by the Casimir of second Poisson algebra Q52, and which I showed you. So we have this description. And also we can interpret it in terms of the following general notion of Cremona transformation, which you know very well. So it is just a rational birational transformation of CP n, projective space of dimension n, such that the direct and inverse map are both rational. Such transformations are very important. They are people try to classify them, describe them, and classical problem of algebraic geometry of end of 19th, early 20th century was to describe Cremona transformation in P4. One of the class of this Cremona transformation was so-called quadracubic Cremona transformations, transformations which are in one sense quadratic, in opposite sense cubic. And this is exactly the quasi-classical level of this Odesky-Fagin subalgebra embedding. So let's consider quadratic Cremona transformation given by polynomial phi with composition with composant phi 0, phi 4. Each composant, it's a quadric, degree 2 in 5 variables, and we have a parameter on P2, lambda and mu, such that my previous k, it is lambda over mu, and a family of elliptic curves, which is given by so-called Klein quadrics. So I put here blue because I want to show you some picture in Russian, and in this picture, this y lambda mu will be denoted by another in another way. So just remember this. So we have this Klein quadrics. It is very easy to check that these quadrics are 4 times 4 Pfaffian of so-called Klein's CZG 5 to 5 skew-symmetric metrics of linear form. And also they have very nice geometric interpretation, like singular and non-singular fibers of the following elliptic fibration. So you have a fibration over P1 with coordinates lambda and mu, and these fibers are elliptic curves given by these 5 to each lambda and mu. You have 5 quadrics, which gives you a local complete intersection, normal quintic. So we have singular and non-singular fibers depending on lambda and mu, and the total space is so-called Horrocks-Mumford surface. And I will want to say that the inverse application, that inverse Cremona transformation for this big phi, phi minus 1, is given by cubics. And this cubics gives you the surface of quintic elliptic scroll, which we have discussed in symplectic foliation. So we have symplectic leaves which are given by secant of y in P4, and the scroll which is a symmetric square of y in P4. And this cubic polynomials, they give you a quadric-cubic family of Cremona transformation, which was described in the first time by Semple in 1926. So we have the following theorem: the quadricubic Cremona transformation, classical quadricubic Cremona transformation, they are birational Poisson morphisms of P4, which transform Q51 to Q52 and vice versa. But we should change the families of elliptic curve, lambda, mu, and by mu minus lambda for Q52. And this Cremona transformations, they are quasi-classical limit of Adesky-Fagin quantum homomorphisms from P1 to Q52 and vice versa. How to find this centrum Casimirs, which gives you this symplectic foliation? Very, very nice. You should just compute this Jacobian of this transformation of quadric transformation, and determinant of Jacobi matrix. Or this matrix also people called in old-fashioned school, they called polar matrix, this matrix of Jacobian, this polar matrix of the family of quadrics. And the determinant gives you exactly the quintic K51. And Jacobian of inverse transformation gives you a family of four-dimensional symplectic leaves of this algebra Q52. So you have in Q51 four-dimensional symplectic leaves given by this Jacobian and this by this Jacobian. They are similar, but they are different, because the second matrix, this matrix comes from Klein CZG, and this matrix, I mean this these quadrics and these cubics, they came from so-called Moore CZGs, which was described in his thesis, Australian mathematician Robert Moore in mid-70s. So the picture graphically, you can just more precisely imagine this full picture of this. So you have elliptic curve y in P4, and you have the secant of this elliptic curve in P4. Then you have this scroll S2 of y in P4, and you have this 3-secant of this scroll in P4. So the Cremona transformation phi from, hat means that you need to be very, very rigorous. You should take blow up, of course, over these divisors given by the, because I was not very precise, but in fact, this Cremona transformation, phi and phi minus 1, they should be defined on the blow up of the corresponding projective space over the corresponding divisors. So you have this Cremona transformation phi, you have this Cremona transformation phi minus 1, and you have transformation of blow up of secant to trisecant, and you have f minus 1 of blow up of trisecant to secant. So this is a full geometric description of symplectic Cremona morphisms. Now I want to show you the condition that Cremona transformation is a really Poisson morphism between Q51 and Q52. First, I want just to take Q51 and to impose H invariant quadratic constraint to image with phi of this bracket. And this constraint gives you the following algebraic system. This algebraic system has two classes of solutions, and one class of solution is absolutely fantastic because all people who read in use the book of Klein lectures about icosahedron, they know this equation. And now it's I'm sorry for non-Russian speakers because I supposed to make a translation with my pen, but now I just explained that this is a Klein icosahedron, and it is a beautiful object which relates to geometry, Galois theory, group theory, invariance theory, and differential equations. And one can find very deep appearance of this object in all cases. In our case, this icosahedron just gives you description of our quadrics, which, remember, I denoted by blue Y. Here it is denoted by C lambda mu. So each vertex of icosahedron, it is a singularity of this family of quadrics. So you have this 5 quadrics given by this line, but each vertex, it is a degeneration. So each point in your icosahedron, each point in your icosahedron gives you the family of quadric. It means the family of Poisson structures, and you have some degeneration. So we have these pentagons, which I took from the beautiful book of Hulek, and these pentagons, they correspond different configurations of this quadric and their degeneration, and each one has analog of Odesky-Feygin-Sklyanin algebra Q52, but in these vertices, these algebras, they are no more elliptic, they are rational, and these rational algebras, they can be described sometimes very explicitly in the infinity, and in zero, these algebras can be described like how to say, like cluster algebras. So this relation with cluster algebras, no time to discuss. And the last, what I want to say, that all this beautiful picture can be generalized, of course. I don't know full generalization. It is still a very challenging and interesting problem. But for n equal to 7, the next interesting case, we have 3 non-isomorphic Odesky-Sklyanin-Feygin elliptic algebras, 7, 1, 7, 2, 7, 3. Why we have no 7, 4 or 7, 5? Because there is a theorem which was proven also recently rigorously by Smith and his collaborators, that n comma n minus 1 algebra, it is just isomorphic, it is abelian polynomial, and n k isomorphic n k prime when k times k prime comparable with 1. So we have only 3 independent algebras for n equal to 7. They are not isomorphic between them, but we have no 7, 5, for example. Instead of 7, 5, we have 7, 2. Anyway, there are the following interesting objects we can consider for n equal to 7. 3 Heisenberg invariant elliptic septic YA in P6, and they parameterized by Klein quartic surface. Instead of P1, now we have the Klein quartic. And also, if we have a cuspidal point of this quartic, then these elliptic curves degenerate to configurations of line. And this algebra also gives you a rational degeneration of elliptic algebras. So we have three invariant elliptic ruled surfaces. So we have a sequence of each y sub a. And also we have 7 quadrics which contain this surface, and these 7 quadrics, they are Pfaffian. They give you Cremona transformation between these 3 algebras. I know equation, explicit equation, only one of this couple. I was not so strong in computation that to write explicitly full 3 Cremona transformations and the inverse Cremona transformations for all. I know only transformation in one way between 2 algebras. So if people know how to, well, it is a question of Mathematica or Maple. I'm not very strong in this. So thank you very much.
Thank you very much. Any questions?
Yes, I have a question. May I?
Sure.
Volodya.
Yes.
Though you told almost nothing about this relation, the algebras are related to integrable systems, yes?
I told you that there is
yes, you told, but scarcely. But never mind.
No, it's another subject, Joseph. It's another subject. If you want...
I don't want to discuss. I want to ask a question.
Yes.
These systems are 1 plus 1, yes, two-dimensional, or not only.
These systems, the systems which I know, which appeared in this context, they are, how to say, I know a beautiful example, and they are a system of, it is a kind of statistical models, RSOS statistical models.
But initially, Sklyanin...
of boundary conditions, so-called Felder-Warchenko boundary conditions.
Well,
this is application which I did. And also I know how to interpret in these terms integrability condition in terms of I can reduce this algebra for n equal to 3. I can reduce this algebraic abelian object in terms of Fay identity.
What is n in terms of integrable systems? Well, Sklyanin initially...
for me, n in terms of integrable systems, it's a number of commuting Liouville commuting variables, functions.
Okay, but well, Sklyanin initially was not interested in algebra. He was interested in integrability of differential.
No. Sklyanin got algebra from the from solutions of inverse scattering problem. That's true.
Yes.
But he discovered that the object is quite interesting and might be also very. I know many degenerations of Sklyanin algebra related, for example, to top. There is a so-called Sklyanin top. I can show you with n equal to 3 generators. There is a Sklyanin generalization of top.
These are ODEs, but he was, well, when he was interested in PDEs. Or not?
Well, it is Liouville integrable system for me. That's all.
Finite dimensional.
Finite dimensional.
Okay, thank you.
Finite dimensional.
Thanks a lot.
Any more questions? Well, if no, let us thank Volodya. Thank you very much.
Well, thank you for your patience. But I don't understand what's happened with my voice, Misha.
Well, I don't actually